Welcome to Empowered Learning. This is the third video in the video series for Power Series. So in this video, we will learn how to find equivalent ways of writing certain functions as sums of a power series. Specifically, we will learn how to represent these functions as a power series by manipulating the list of these sums of a power series in one of three ways. So the first way, which is probably going to be the most important way that we do it, is by looking at what we're dealing with as a geometric series. The second way is we're going to differentiate the terms of the power series to get the desired function. And the third way is we're going to integrate the terms of the power series to get the desired function. So why are we doing this anyway? Using the strategy to represent certain functions as a power series will actually make it easier to do the following things, which include, but are not limited to, what I'm about to say here. First, integrating functions that do not have elementary function-like antiderivatives. In other words, an antiderivative can't be found by known integration techniques that are taught in a first and second year calculus course. Such things as U substitution, integration by parts, trig substitution, partial fraction expansion, trig integrals, so on and so forth. Okay. Now, if you were actually evaluating a definite integral and you couldn't do it by any of the methods that I listed, then of course you have things like Simpson's rule, trapezoid rule. You can do the Raman sum estimations. You could do all that. Okay. But in general, if we just want to know what is going to be the function that's going to be the antiderivative for the thing that we're trying to integrate, of course, things like numerical integration, like the trapezoid rule, Simpson's rule, doing Raman sums, that's not really going to help us out. Okay. So that's why it's important for us to kind of go through this. So another thing that will make things easier for us, or things that we can use a power series for, is to represent a function over a certain interval as an equivalent or approximating polynomial function. And this is like the core reason why we have and use power series. So for instance, in your calculator, so if you have a graphing calculator or whatnot, let's say if you wanted to calculate what sine of 2 radians was, or let's say you want to calculate what sine of 2 degrees is. Okay. Of course, you have to change the 2 degrees into radians to be able to calculate it. But the thing is that your calculator does not actually have a sine function in there. Okay. And saying, hey, you just put in 2 degrees. What your calculator has is a polynomial approximation of what sine actually is, up to a certain number of terms in the polynomial that approximates it. And then when you plug in, let's say 2 degrees or 2 radians, depending upon what mode you have your calculator in, what it will do is it'll accept that x value, plug it into that polynomial, and then spit out an answer based upon the number of decimals after the number of digits after the decimal it can actually hold in that particular calculator. So that's actually what's going on. So again, all that comes from being able to represent a sine function and other functions as a power series. Okay. All right. So moving on here, we can also simplify expressions in several different formulas that derive from scientific experiments. So for instance, if we're trying to characterize some data and we're looking at it and we're like, hey, don't really know what this looks like as far as some of the regular functions that we learned from, let's say, pre-calculus. What we could do is to say, all right, well, we know that any smooth and continuous function, if we approximate our data to be smooth and continuous, can be approximated as a polynomial. And so we just use that information to do it. Okay. Another thing that we can do is to help express difficult looking functions on a calculator or computer in an easier way. And that was the example that I was giving you as far as like the sine of 2 degrees or 2 radians. I didn't write this here, but another thing that we can do is we can take the limit of certain functions. Okay, so for instance, one of the things that you see in first year calculus is that the limit of, let's say, sine of x divided by x, we're told that that is equal to 1. Okay, and of course, you learn that, hey, you can evaluate this limit here by doing L'Hopital's rule, or if you just know what the graph of this particular function looks like, in this nickname here is a sinc function. If you know what it looks like, then you know that the graph of it at 1 has a hole in it and it kind of does like this. You do it that way. But if we wanted to do it from a pure algebraic sense, or pure computational sense here, the way that we would do that is that we would take this sine function, express it as this approximating polynomial, and then take that polynomial, divide it by x. And then if we do that, what we'll see, and you'll actually see this in later videos that I've made here when we talk about Taylor series and Maclaurin series, you'll see that that very first term, when we express sine of x divided by x as a polynomial, will be 1. All the other terms will have x raised to something in it. And then, of course, if we take the limit of 1 plus or minus all other terms that have x raised to something in it, all the other terms are going to go to 0. And you just have that one term left with just 1. And that's how it ends up being there. Okay. So again, for situations where we have functions like sine of x over x, where we want to take the limit of it and we want to kind of do it in a purist fashion, the power series is sort of our loophole to get us to a form of the function that we could use to be able to easily evaluate the limit of. Okay, so what we're going to do next here is we're going to do several examples displaying how to manipulate certain functions as a geometric series. And so this statement was made here in these notes because most of the problems that we do, since the geometric series is relatively easy to deal with, and we already know what the sum of a geometric series is, it's advantageous for us to try to take a function that has the potential of being formed into a geometric series, to try to fit it into that form, so that we could really write it as a geometric series, and thus from a geometric series transform it to a power series, which is just a change in index or a change in the counter, depending upon what you want to call it. And from there, we'll be able to have a polynomial approximation for it. Okay, so hopefully some of these examples that I do will sort of illuminate that in a way that you can understand. So let's look at our first example here, which is example number 1. We want to represent this rational function 2 divided by 3 minus x as a power series. Okay, and of course my hint here is that we want to use the geometric series to help us out. And then after we do that, let's find the interval of convergence. So as a reminder here, our geometric series, if it's written in sigma or summation notation, it looks like a times r raised to the n minus 1, where we know a is the first term of the geometric sequence, and r is the common ratio in between each term of the sequence that makes up this series. Okay, and of course that goes from n equals 1 to infinity. If we add up all the terms of the geometric sequence, we get the geometric series. And of course, we know that that sum converges to a divided by 1 minus r. So it's important for us to know what the first term of that particular series is and what the common ratio is. And we know that all geometric series converge as long as r, which is our common ratio, is going to be in between -1 and 1, and it diverges otherwise. So here, what we do is we take our function here, and we want this to look something like a divided by 1 minus r. So to do that, I need a 1 right here in this spot. So I force this 3 to be factored out, so I can force a 1 there. And then what I see is I could rewrite this as 2/3 in the numerator. Then I'll have 2/3 divided by 1 minus x divided by 3. And this fits the profile of a divided by 1 minus r, where a is 2/3 and r is x divided by 3, or 1/3 x. Okay, so in this sense, we know that our function now can be represented as a geometric series where 2/3 is a, r is x divided by 3. If we want to, we could factor out that 2/3 at this point and just leave it here, leave the rest inside. And at this particular step, we're converting from a geometric series to a power series. And all we do here is we change our counter, or our index here, from n equals 1 to n equals 0. Okay. And when we change that, that also changes this exponent here, going from n minus 1 to n. Okay. Now, of course, why this works that way is if you look here, when n is equal to 1 and we plug that into here, we know 1 minus 1 is 0. Okay. So we have to replicate the same thing here. And if we change our index here to n equals 0, then we still got to have 0 up here, which means that in order for that to happen, we have to have n instead of n minus 1. So again, making this step from here to here by changing the index, that gets us from geometric series format to power series format, which is what we need. Okay, so once we have that in place, then everything else is pretty easy to do, because we have what we want, which is our function in power series form. Now all we have to do is figure out what is going to be our interval of convergence here. So we see that our interval of convergence for f of x is going to be whatever this x divided by 3 is, as long as it's in between -1 to 1. So in terms of x, that's going to be values of x specifically in between -3 and 3. Okay, and in this sense, we don't have to go and test the n values -3 and 3 to see if they're going to diverge or not, because remember, our function was forced to take on the form of a geometric series, and we just sort of changed the indices and make the geo series look like a power series. So remember that this function here is still a polynomial that's really a geometric series. So we automatically know that at x equals -3 and 3, it is going to diverge. Okay, so there's no need for us to actually test it because we already know what the outcome is. And so we're done with this particular problem here. We know what the interval of convergence is. It's going to be all values of x in between -3 and 3. And we know how we could express this function 2 divided by 3 minus x in power series form, or put it another way, as a polynomial written in compact form. And it looks like this. Okay, and so that's all there is to that. So let's look at another example. Okay, so for our next example, we see that we have a function that looks a little bit more difficult than the one that we had before, and that's okay, but our goal is still the same. We want to be able to represent this rational function as a power series and then find out what the interval of convergence will be for. So we're going to take the same approach as we did last time. We basically want to force this particular function here to look like a divided by 1 minus r. Because if we do that, then of course we know we could express this in geometric series form, looking like this, where n here is equal to 1 and goes to infinity. Okay, so we already have the 1 here, so we could really kind of look at this as 1 plus 2x squared. And what we want to do again is force this to look this way. So to do that, we know that this plus here, we're going to have to look at minus, make it look like minus a negative. okay? And so we also see here that we have x in the numerator. And so the good thing about having x in the numerator this way is that we know that this a here is going to have to be a constant, but x isn't a constant, okay? It could be several things. So what we want to do is separate that from the actual portion of this function that we're going to force to be a geometric series. And then after we do that, we're going to multiply it back in. So it's going to make it easier for us to deal with that way. Okay. So if we do that, then of course we see what we have. This portion here can look like the a divided by 1 minus r that we need from the geometric series, where a is going to be the constant 1 and r is going to be a negative 2x squared. So again, if we follow this formula here for what the geometric series is, this will be our a, this will be our r, and of course our x here, to the summation operator, the x looks like a constant, so that's the reason why we're able to take this x that's right here and factor it out of the summation notation that we have. Of course, we can put it back in whenever it's convenient for us. But of course, when we do that, then of course we have this x on the outside, and we just algebraically manipulate what we have going on here. And we're basically separating the negative 2 and the x squared. So the negative 2 is raised to the n minus 1 times the x squared is raised to the n minus 1. Okay, so this will look something like that if I was actually writing everything. So if we are looking at this, of course, this is in the geometric series form. We need to change it to the power series form. And power series start with the index of 0. So that means, again, if we change this from n equals 1 to n equals 0, then it means my n minus 1 here has to change to n, and my n minus 1 here has to change to n. Okay? And so notice that I did that, and I also took this x that was here and now put it back in. So that's why you see the extra x right there. Okay, so now that we have all that in place, and now we have our geometric series now looking like a power series, then of course this x here is the same as x raised to the 1. So this means the same as x raised to the 2n plus 1. And of course here, we could rewrite negative 2 as a negative 1 times a positive 2, so that we can get this alternating sign factor here. And so now what we end up having is just the power series, where the internal sequence of that is just going to be, well, the internal family of sequences, I should say, is going to be a negative 1 raised to the n times 2 raised to the n times x raised to the 2n plus 1. Okay, so that is what our function x divided by 2x squared plus 1 would look like in power series form, or aka looked at in the as a compact polynomial form. And the interval of convergence, remember again, this is a geometric series. So whatever this is going to have to be in between negative 1 and 1. Okay, so here, another way of saying that is that whatever r is, the absolute value of it has to be less than 1. So that's what we have here. And of course, with this algebraically manipulating all that, we get to the point where we essentially have the absolute value of x squared has to be less than 1/2. Of course, I deal with this with the square part of that. Of course, absolute value of x is just going to be less than or equal to 1 divided by square root of 2, or root 2 over 2. And thus, at this point, we know that x is just going to be in between negative root 2 over 2 and positive root 2 over 2. Okay, So that's what x has to be in order for this particular function here to converge. So as long as we pick values of x and that we plug in that are in between those two values, we're good to go. Okay. And what we would see here is that these x values, if we plug them into this function here, the polynomial that we have right here would give us the same value as we would if we were just plugging them in here. Okay. Now, if I was to, let's say, plug in a 1 for x, well, that's not going to work here because 1 is not in the interval of convergence. So we have to strictly stay within the x values that we have in order to have our polynomial match up with what our function that we tried to express as a polynomial would be exactly. Okay. Okay, so the first two examples I had already worked out for you, but these next two examples we're going to work out from scratch. So you can kind of see how this is done organically from the beginning. So we want to represent the function 1 divided by x divided by 1 plus x as a power series, and then also find the interval of convergence. So remember, the main thing that we want to do here is try to manipulate our function to look something like the sum of a geometric series, because if we can do that, we can easily figure out what the a and what the r is and force it to be some compacted polynomial, okay, aka put it in power series form. So to do this, notice that our function f of x could actually be written as the difference of two functions here. So we could rewrite this as 1 over 1 plus x minus x over 1 plus x. Okay. And so this is good because now what we could do is rewrite this as a sub 1 over 1 minus r1 minus a sub 2, 1 minus r sub 2. And so all we have to do now is figure out what a sub 1, r sub 1, a sub 2, and r sub 2 would be. Okay. So here, if we want to get this in this form for this first one, we could have 1 over 1 minus a negative x. And that would get that in the form that we would want to have it in. And then minus, I'm going to do x times 1 over 1 minus a negative x, like that. Okay. And so what we actually see that we have here, we could either split it up as 2 or just make it 1. I'm going to try to do it as 1 here to cut down on the amount of work. We could actually look at this like this, and I'm just going to write this for now. We could actually just look at it this way. And then have it look like this. Okay. So if we look at it like that, then we could look at this as just like one geometric series here, where our a would be 1 and our r would be minus x. And then rewrite this as a power series and then multiply the answer times 1 minus x. That's one way that we could do it. Okay. If we wanted to look at it the other way here, like kind of how I have it here, and I'll kind of do it both ways. This could be my a sub 1. This could be my r sub 1. This could be my a sub 2. That could be my r sub 2. And as you see, a sub 1, a sub 2, r sub 1, and r sub 2, the a sub 1 and a sub 2s are the same. The r sub 1 and r sub 2s are the same. So that's why once I kind of saw what was going on here, I just elected to kind of do it like this. Okay. And so that's the way we're going to stick with it. So we're going to say here in general, I'm going to go ahead and change this up here. Just kind of make this a little bit more simple. Let's just say here we want this as 1 minus x times 1 over 1 minus a negative x. Okay. And we're going to say this could be rewritten this way. Okay. And I'm going to erase all this other stuff here now that we kind of see what's going on. And we'll write our a as 1 and our r as a negative x. All right, so I've written down here that we can look at our function here as just as 1 minus x times a divided by 1 minus r, where our a is going to be 1 and r is going to be equal to a negative x. So therefore, we know that f of x can also be expressed as 1 minus x times this geometric series. And this will be the geometric series a times r raised to the n minus 1. And so to change this geometric series to a power series, what we need to do is change our index from n equals 1 to n equals 0. And of course, in doing that, what that is going to change is the n minus 1 in the exponent to just be n. Okay. And so from here, we also know that this minus x here could also be expressed as negative 1 raised to the n times x raised to the n. So I'm going to go ahead and erase what I have here. Change that. And so that way we have the alternating factor here kind of separated from everything else. And so that is what this would look like. And so now we could go and actually bring in the 1 minus x now, okay? So this would be negative 1 raised to the n times x raised to the n times 1 minus x. Of course, if we keep going here, we go ahead and distribute that x raised to the n in both terms, then we're just going to have x raised to the n minus x raised to the n plus 1. And that is what this particular function would look like in its power series form. Now, what is going to be the interval of convergence? Well, if you remember here, whatever r is, it's going to have to be in between negative 1 and 1, okay? So here, how we would express that absolute value of x here would have to be less than 1. Of course, we don't know what x is going to be, but we know that absolute value of a negative x would just be absolute value of x. And that's because we could rewrite absolute value of negative x as this, which would be absolute value of negative 1 times absolute value of x. And so, of course, the absolute value of negative 1 is just 1. 1 times absolute value of x is x. So we have the situation here. And this essentially means that x is in between negative 1 and 1. So, of course, our IOC now is just going to be the x values in between negative 1 to 1. So, we know that our function f of x can be expressed as a compacted polynomial in this way, aka as a power series, and we know that our interval of convergence here is going to be -1 to 1. And again, I want to stress that we don't have to check for convergence at the end values of this interval of convergence here, because we forced our function to be a geometric series, and we already know that the geometric series will diverge at those end values. Okay. All right, so let's look at another example that we can work out from scratch. Okay, so for this example, we have the function x squared divided by a cubed minus x cubed, where a is some constant. We don't know what it is, but it's just a constant real number. And we want to express this as a power series and find the interval of convergence for the power series. So again, our goal is to force what we have here to look something like the sum of a power series, which is a divided by 1 minus r. So that is the main idea here. So in looking at this, the first thing that we see here is that we have a x squared in the numerator, and that's really not going to help us with the whole trying to force this thing to be a geometric series. So what we're going to do is just leave that part out in front and then just deal with the 1 divided by a cubed minus x cubed and try to change that into power series form. Okay. Now to do that, of course, we want this to look like a divided by 1 minus r. So where we have this a cubed, we need a 1. Okay. So a way that we can force that to happen here is we can multiply the numerator and denominator of this 1 divided by a cubed minus x cubed. We could take this, multiply it by 1 divided by a cubed over 1 divided by a cubed. Okay. So if we did that, then what that would leave us with here is x squared times 1 over a cubed in the numerator here, and this will be 1 minus x cubed over a cubed in the denominator. Of course, if we wanted to go a little further here, this would be the same as what I'm writing here. So we could take that x cubed divided by a cubed and just write that as x minus a quantity cube. Okay. So once we have this in this form here, then we pretty much have everything that we need to write this as a geometric series. So this is going to be, I'm just going to call it my a sub 1 here since I already have an a there. And I'm going to call this my r. Okay. And so, of course, remember our geometric series, we want this summation of a sub 1, in this case, r raised to the n minus 1. N starts at 1, goes to infinity. So that's what we're trying to form this in. So now that we have that, therefore, f of x can now be written as x squared times summation n equals 1 to infinity of our a sub 1, which is just going to be 1 divided by a cubed, times r, which is x divided by a raised to the 3. And that's going to be all that raised to the n minus 1. Okay. And so now at this point, all we need to do is do the best that we can to try to simplify what we have on the inside of the power series, or the sequence part of it, and then bring in the x squared to try to round everything out and make it look nice. So here we're going to keep the x squared out for now. we need to change this geometric series into a power series. So we need to change our index here from n equals 0 to n equals 1. And so basically what that's going to do here is change our exponent from n minus 1 to n. Okay, so we're going to have that. And then, of course, from there, it's going to come over here and we'll finish trying to make this look as simple and as nice as possible. So here we'll have 1 over a cubed times x raised to the 3n over a raised to the 3n. And here we can go ahead and bring in that x squared now. And so this will be x raised to the 3n times x squared over a raised to the 3n plus 3. And then from there, this will be x raised to the 3n plus 2 over a raised to the 3 times n plus 1, like that. So at this point, as far as the power series is concerned, it's okay to leave it like this, but I'm going to go just a little bit further here. And here, one of the things I notice is that, of course, this a raised to the 3 times n plus 1, of course, that's all in a denominator. We can look at this as 1 times all of that. And here, if we were to look at it this way, that's a little bit too small, so I'm going to try to write it just a little bit bigger here. So just dealing with this portion here, we know 1 raised to just about anything is going to be that. So I could look at this as 1 raised to the n plus 1 as well. And if I looked at it that way, then I know per my exponential rules, I could have this as 1 over a raised to the 3, and then all that raised to the n plus 1 that way. So I'm going to rewrite what I have here in this last step so that I can have the 1 divided by a cubed, all that raised to the n plus 1 there. So that's an alternative way that we could write all of this. So I'll just change that, and then afterwards we'll go ahead and find out what the interval of convergence is going to be. And then we'll go ahead and move on from there. So this is 1 divided by a cubed, all that raised to the n plus 1, and then that is multiplied times x raised to the 3n plus 2. Okay. And so this is what our final answer would be for our power series. Of course, for our interval of convergence, remember that our r that we had, our r there, and I think I circled the wrong thing here, so let me make sure that this is correct. Yeah, so you erase this part here. So this is supposed to be x minus a cubed. And so I didn't circle all of it, but all of this is supposed to be the r. Okay. And so with that, we know that r has to be, absolute value of r has to be less than 1, or essentially this x cubed over a cubed absolute value of all that has to be less than 1. Okay. So if we look at that in another way, this is essentially going to be where x cubed, absolute value of that, is going to have to be this. All right, so looking at the situation here, if I go ahead and take the cube root of each side, then I'm just going to have absolute value of x is less than absolute value of a. And so, of course, by definition, this means that x is going to be in between a negative absolute value of a and an absolute value of a. And so we don't know what a is, so that's why we have to keep it general like that. So our IOC is just going to be the x values from negative absolute value of a. Make sure I do the absolute value signs here. Just trying to do it over. So negative absolute value of a to positive absolute value of a. And that is what our interval of convergence would be there. All right, so let's move on. So now that we've seen a few examples of how to take a function, and mostly these functions were rational functions, and rewrite them as polynomials, aka as a power series. Now we want to discuss differentiation and integration of a power series and how we will perform these operations on a given power series. The following theorem, which we'll call the power series differentiation / integration theorem, will allow us and also show us how to do differentiation and integration operations to a power series. In short, this theorem says that if a power series has a radius of convergence that is greater than 0, then we can differentiate or integrate the power series by taking the derivative or integral of each term of our power series. And remember that our power series is just a compact way of expressing a polynomial with an infinite number of terms. Okay, so let's go ahead and look at what this theorem actually says. So we have the power series differentiation / integration theorem. And it says that if the power series that is in general written in this form, so we have the coefficient c sub n, and the power series is centered about some value x equals a, and it has a radius of convergence that is larger than 0. So in other words, we're not considering a power series that only has one x value that will have an infinite series that will be convergent. We're looking at more x values than that. So we have a radius of convergence that is greater than 0. Then the function f that is defined by, and we're basically saying here that we are listing out term by term what the power series is. And we're assuming here that this particular function can be represented as a power series. So if this function that we want to represent as a power series is differentiable on the interval of convergence here, and of course, depending upon where it's centered at and what the radius of convergence is, that'll let us know, then we can do the following, okay? So we got to have a function that is differentiable on the values of x that fit within this radius of convergence here. And of course, if we want to take that function as expressed as a power series, then we know that if we take the derivative of this function, if it's in its power series form, then what we can do here, after we kind of list everything out, is we can just take the derivative of each term. So if I go back up here, just to kind of make my point, if I take the first derivative of the first term, that's going to be 0. If I take the first derivative of c1 times x minus a, that's going to be c1. And of course, the derivative of x is 1. The derivative of a constant is 0. If I take the derivative of the next term using the chain rule, I'll have 2 times c2 times x minus a. the next term I'll have 3 times C3 x minus a squared. And of course, the derivative of the inside function here, x minus a, would just be 1. So that's why I'm not writing anything else. And of course, this would keep on going forward here. So if we look down here, this is essentially what I'm saying. If we take the derivative of this power series, it's going to look something like what we see here. And notice now that we start at C1 instead of C sub 0. So that means that our index for our summation operator here, or you may call it the counter, is going to start at n equals 1 instead of n equals 0. And of course, that's because in doing the derivative, we lose this constant term, okay, in doing the derivative there. So we're like 1 term less than what we originally had for the original function. So we know that that's how we would differentiate this function in its power series form. If we were taking the most general antiderivative of the function, then we would, of course, use the power rule for integration for it. So coming here and kind of doing the same thing. Let me erase this here. So if I was going to take the most general antiderivative of a constant, it's just going to be that constant times x. If I take the most general antiderivative of C1 times x minus a, so this is going to be C1 times x minus a squared over 2. I'll do it here to the next term. That is going to be C2 times x minus a raised to the 3 over 3, and so on and so forth, okay? And so that's essentially what we see here. Now, of course, I forgot to write the x minus a right there. But in addition to all of this, because we're taking the most general antiderivative, we also have an integration constant that we have to add as well, okay? So we see here that most general antiderivative would be this constant, and of course we would have to know something about what the antiderivative of the function is, like a point on its graph or something. And then of course we have this situation here where we can express a power series is just c sub n times x minus a raised to the n plus 1, all that divided by n plus 1. And again, essentially all we're doing in this case is we're taking this portion here and we're just saying, all right, we're going to apply the power rule. And that's pretty much all it is. So that's what you see down here. Now, how this is actually going to work for us is that there are going to be some functions to where if we try to rewrite it and force it to be a geometric series like what we had been doing before, it's not going to work out too nice for us, okay? But we're going to see that there are some functions where if we take the derivative of that function or we integrate that function or take the antiderivative of it, its derivative or antiderivative would be in a form that is conducive to us being able to work with it so that we can express that as a power series. And then we'll either, in the case of taking the derivative of a function, we'll undo it by taking the antiderivative of the power series. Or in the case of when we took the antiderivative of the function, we would take the derivative of the power series to get back to the original function. And of course, that will be in power series slash infinite term polynomial form, okay? And so that's the main thing that we're going to do right now with these, with the power series and this power series differentiation slash integration theorem. All right, so for our next examples here, we want to find the power series representation for our functions and determine the radius and interval of convergence of the power series. So the function that we're asked to deal with is natural log of 5 minus x, okay? Now, of course, natural log of 5 minus x is not something that we can look at and say, yep, I'm going to force that to be in geometric form. However, I know that if I take the derivative of natural log of 5 minus x, I know that's just going to be 1 over 5 minus x, okay? And of course, that times the -1 here because of the chain rule, which is just going to end up being a -1 divided by 5 minus x, okay? Now, this is something that I can work with to force to be in a geometric series form, okay? And of course, if I factor out the 5 in the denominator here and rewrite it like this, and then move this 5 up to the numerator to have this be a -1/5, then I have a situation here where I can let a be -1/5, and I can let my common ratio r be x divided by 5, okay? So if I have that situation here, then I can essentially express the derivative of this particular function as a power series. And then once I figure out what that power series looks like, I can undo the derivative to get back to the original function just by taking the antiderivative of the power series, or just taking the antiderivative of each term of the polynomial, okay? The infinite series polynomial that we have, okay? So looking at that, we know that the derivative of natural log of 5 minus x, we know that we can express this way here. And this is our a, this is our r. Express this as a geometric series. Notice that the index changes from n equals 1 to n equals 0 to get it into power series form, which also means that this n minus 1 changes to n. And then after that, we have all that together. So now we say that the integral of the derivative of natural log of 5 minus x, which I'm just kind of starting from the beginning and working there. Now we want to take the antiderivative of this particular power series, which is the same as this, because remember what we want is the original function, and what we have is the derivative of the original function. So we're going to change the way that this looks here. And to do that, I separate the 1/5 and the x here. And I do that so that I can work on this part in using the power rule for antiderivatives, which basically means I'm going to add 1 to the exponent, divide by the same. And that's essentially what you see here. And so what we end up with now is essentially what the function that we want to be is in terms of power series. So this is what natural log of 5 minus x is going to be. Now, another thing that I want to mention here is that, of course, in figuring out what this particular function, natural log of 5 minus x, is in terms of power series, we still have not identified what this integration constant is going to be. And so here we can actually figure that out by studying some basic information about our function, natural log of 5 minus x in the first place here. Now, one of the things that we have to understand here is that this natural log of 5 minus x, I'm just going to write this in general here. We know that this is some constant times some constant here times was it x raised to the 1 plus some other constant x squared plus some other constant x cubed, so on and so forth. Okay. Now I know it's not exactly what this is, but I'm just doing this to make a point here. Now, if we know that this function here is going to be modeled by a polynomial, then we know that all the terms that have x in it, which is really the thing that I'm trying to get at, if we were to plug in 0 in for x, then of course all of these terms except for the one with the constant is going to go to 0. Okay, so here what we can do to find out what our integration constant is we can just figure out, well, what is natural log of x minus 5 when x is 0? And that's going to tell us what our constant is. So if we do that here, you see that the result here is just natural log of 5. whatever that number is, okay? So here, now that we know that our integration constant here is just going to be natural log of 5, we can replace that for c. So this is where the integration constant c was. Now we have a natural log of 5 there. And so now we have everything that we need to be able to express this function, natural log of 5 minus x, in terms of a power series, okay? And so, of course, we have this constant here, minus, of course, power series. And, of course, we know that let's go back up here. We know that our common ratio, because we forced this to be in geometric series form, is just x divided by 5. So here we know that the common ratio, absolute value of that, has to be less than 1 in order for the power series to be convergent, which inevitably means that x divided by 5 has to be in between -1 and 1, which means x has to be strictly in between -5 and 5. And so, of course, that is going to be our interval of convergence for this particular power series representation of the function natural log of 5 minus x. Again, this is what the final representation of natural log of 5 minus x would look like. All right, so let's move on to another example. So in this next example, we want to express the function natural log of 1 plus x divided by 1 minus x as a power series. Now, again, trying to do natural log of anything and force it to look like a geometric series is not something that we can do, it's not something that we want to try to do directly. But here we do know that we could rewrite this function as natural log of 1 plus x minus natural log of 1 minus x. And thus, we could take the derivative of natural log of 1 plus x and natural log of 1 minus x, and it'll be something relatively easy for us to deal with that we can kind of force into looking like the sum of a geometric series. So here we see that, of course, this function here can be rewritten just like how I wrote it up here. And if we take the derivative of it, the derivative of the first term is just 1 divided by 1 plus x, minus derivative of the second term is a -1 divided by 1 minus x, which in turn is just going to look like this. And of course, we're rewriting this plus x as minus -x because we're trying to set it up to look like a geometric series, okay? And for here, this is going to be my a sub 1. This is going to be my a sub 2. The minus x is going to be r1, and the positive x is going to be r2. And so that is what I was writing here. And of course, we know that the sums here is going to look like a sub 1 divided by 1 minus r and a sub 2 divided by 1 minus r2. So we can now rewrite everything the way that we need to. So here we know that if we take the derivative of the function that we're originally looking at, and we take the antiderivative of it, is going to equal what we started off with some integration constant, okay? So let's work on making this and this look like a power series, and then take the antiderivative of both of those power series, and then add up the answers. So for our first term, it's the sum of a geometric series where our a sub 1 is 1, r sub 1 is minus x. And of course, after we do some rearranging here, we see that this 1 here could be looked at as, sorry, not that 1. Here we have this negative here that's inside of there, and this would look like a 1 times -1 raised to the n minus 1, and then that's times x raised to the n minus 1. And so we have that here, and this 1 and this negative 1 raised to the n minus 1 can combine together, because 1 could be looked at as 1 raised to the n minus 1 as well. So we can combine that together to just look like what we see here. And this is what it looks like in geometric series form, but we need it in power series form, which means that we need to change the index. Okay, so we change it to 0, which means that we're changing the n minus 1s to n's. And so now we have this first sum here in power series form. If we do the same thing for the second term, which is another second sum, then of course a sub 2 is 1 and r sub 2 is just x. And so this is simply just the power series n equals 0 to infinity, where on the inside we have x raised to the n, because again we need to change the index from geo series form to power series form. Okay, so once we have that together, then we know that the answer that we're looking for is going to be the antiderivative of these two sums of the geo series form that we forced these derivatives to look like. And of course, we started off with this, and what we ended up with now are these two terms. And so now all we have to do is take the antiderivative of the x raised to the n part for both of these terms. And since both of these have an x raised to the n in it, we go ahead and factor that out to make life a little easier here. And we notice that this negative 1 raised to the n plus 1 has a special kind of thing going on. Okay, so whenever n is even, like if we had n equals 2, n equals 4, n equals 6, then of course negative 1 raised to any even number is just going to be a positive 1. And of course 1 plus 1 is 2. Now, if we contrast that, whenever n is an odd number, like n is equal to 3, n is equal to 5, of course we'll end up having a negative 1 for that first term, and a negative 1 plus 1 is 0. And so that is what I am saying here. So effectively what's happening is that only the even terms are being counted in this particular power series. All the odd terms, whenever n is 1, 3, 5, 7, 9, we know that those terms are going to go to 0. Okay, so here what we want to do is rewrite our power series in a easier format. And so again, we realize that all of this is going to be 2. Okay, so we'll rewrite that to make it 2, but here also, to make sure that we capture all of the even terms only, we need to change our exponent here, n, to be 2n, because that's going to force us only to deal with the terms where n is even. Okay, and of course, when we do that, we'll get all of the even powered terms essentially. Okay. And so now that we have this in place, we can now take this power series and take the antiderivative of it, or find the most general antiderivative of it, by essentially concentrating on this part and using the power rule for antiderivatives, which basically means we just add 1 to the exponent and divide by the same. Okay, so we have that, and of course we have our integration constant as well. Now, for our integration constant, one of the things that we know here, that if we were to plug in x to be 0 here for our original function, then we know that that's just going to be natural log of 1 at the end of the day, and natural log of 1 is 0. So, and of course, the reason why we're using x equals 0 again is because, remember, we are trying to express this particular function that we started off with, the natural log of 1 plus x divided by 1 minus x. We're trying to express it as a polynomial. And we know that all polynomials have that constant term at the end of it. And of course, we can get that whenever we let x equal 0. So since we know that about polynomials, it's very easy to just try to plug in x equals 0 when we can do it to figure out what our integration constant is going to be. Okay, so in this sense, we know that c is just going to be 0, and all we have to worry about now is our answer, which basically our natural log of 1 plus x divided by 1 minus x is going to look like what we see here. Okay, and so that's what we're saying. And of course, that's with the 2 on the outside there. And of course, if we list out what the polynomial looks like for the first 4 terms, you see that's what it ends up being. Okay. Now, continuing on, we finally found what our function is going to look like in power series form. Now we need to figure out what the radius of convergence and interval of convergence is going to be. So, of course, from the first term that we had, or the first sum that we tried to force it to be a geometric series, we knew that our common ratio was a minus x. So here, we just knew that absolute value of minus x had to be less than 1, which essentially is like saying absolute value of x has to be less than 1, which is just another way of saying x has to be strictly in between -1 and 1. Okay. Now, for the second sum here, we know that x was going to be our common ratio. And of course, absolute value of the common ratio has to be less than 1, which again is just another way of saying x has to be in between -1 and 1. Of course, in this sense, we see that both interval of convergences for, so both interval of convergences for both of these sums are the same. So it makes it very simple of what the interval of convergence would be. If these were different, though, then we would need to take the intersection of both of them. In other words, the x values that they have in common. So here, finally, we see that we have f of x, which is this natural log of 1 plus x of x, 1 minus x, can be expressed as a power series in this form, where our interval of convergence is from -1 to 1. And of course, this is centered about 0 here. So our radius of convergence is going to be half the length of our interval of convergence, which is just going to be 1. Okay. Now, please note here that another way of getting to what it is that we want, we could have taken the derivative of this again, got it into this form, and we could have, instead of looking at it as the sum of 2 geometric series, we could have rewrote this particular sum as just one rational function here. Okay, and using this form of this function, or form of the derivative here, we could have basically wrote this as a geometric series on its own, where 2 is going to be the a, and here the x squared is going to be the common ratio. Okay, and so you see here we would have came up with the same thing. Okay, so what we did up here in doing this problem is looking at it as 2 separate sums of a geometric series. We kind of went at it the long way, but again, we saw that, hey, each term looked like a geometric series, so it made sense for us to do that. But of course, in hindsight, we see that we could have actually made this problem a little bit shorter by just forcing it to be just one quotient and then just dealing with it that way. Okay, so in some of these problems, you do have that option. And of course, if you do that, then of course everything else at this point, once we kind of know, hey, what this is going to look like in power series form, we pretty much deal with it the same way. Okay, so all the stuff that I've written here is nothing different. All right, so from that point, then again, our f of x again is going to pretty much look the same. And now our radius of convergence, we have to figure it out from having absolute value of x squared being less than 1. And of course, since x squared is always non-negative, we can just drop the absolute value signs there, take the principal root of both sides, and essentially we know that x squared is less than 1 whenever x is strictly in between -1 and 1. So again, we got the same interval of convergence here. All values strictly in between -1 and 1. And of course, our ROC is going to be 1. So a different way to approach the problem, get the same answer. All right, so this will conclude. This will conclude this video. I do have some other examples that I do want to show you, but we're going to do that in the next video. So I'll see you for the next video in this series.